So let's build on that discussion we started. RCPs, as we saw, were done by iterating between integrated assessment models and system models. And they were aimed at looking at net radiative forcing that would result from the scenarios, aimed at temperature targets, especially RCP 2.6 aimed for staying below 2 degrees C warming with some 66% probability, and that requires a number of mitigation actions like carbon capture and sequestration, renewable energy options like bioenergy and carbon capture and sequestration, and so on. So you can see that multiple models run over large range, obviously going as high as 2.3, but in terms of determining a target we want to aim for our mitigation and adaptation activities, one has to be careful because emissions, as we said, have been increasing over since the Industrial Revolution over time, and concentrations in the atmosphere also have obviously increased, as we see again and again from the historic emissions here, as well as the business as usual scenarios. So these are in gigaton CO2 per year. What remains, as I said, in the atmosphere in terms of ppm, we are looking here at ppms. You can see the range here. Okay, so greater than 1000 ppm for RCP 8.5 for 172 scenarios, a large number of scenarios. 720 to 1000 ppm for 148 scenarios under RCP 6, and so on. So this is not easy. Do you want to try to cap the emissions, or you want to focus on concentration in the atmosphere and uncertainties that go with it in terms of model carbon cycle in converting emissions into concentrations as well? But even the temperature targets, let's say you chose 2 degrees C target, what exactly does it mean? Does it mean you go below 2 degrees centigrade and you remain there? Or does it mean that you have overshoots allowed over time, that you remain at 2 degrees C with some oscillation? If so, what is the overshoot allowed for how long? Can it overshoot to 2.3 or 2.5 for 1 year, 2 years, 10 years? What will be the local impacts? So those are very difficult questions. In the meantime, the projections are made using these emission scenarios, and there again for projections we have to point out what we already did before. When you look at RCP 2.6 and 8.5 and the stippling, which indicates number of models agreeing with each other, or the consensus, most regions have consensus except over this AMOC region with its peculiar cooling and less warming here, but the polar amplification is clear. But in general, temperature projections, most models agree with each other over all the regions. But as soon as you come to precipitation, there are lots of regions where there is no model consensus. So the difficulty with precipitation continues, and if you have regions which are sensitive already and vulnerable already, and you're projecting precipitation with low model consensus, then adaptation is going to be a challenge. So projections here can be an issue. It's the same for sea level rise. If there is no consensus on sea level rise, how do coastal communities plan for adaptation? What level of sea level rise will they plan for? As I said, there are economic considerations there as well, because nobody can protect themselves against any level of sea level rise. Some navies and so on do, but even they have a limitation on just how much they can invest on protecting against sea level rise. They might be able to do 1 meter and not 2 meters, or half a meter and not 1 meter, and so on. So various considerations are involved. I wanted to show specific example of the monsoon here. So this is observed historic monsoon variability for different months. So you can see where the maximum rainfall happens: August in the summer monsoon season, and in the northeast monsoon season in fall winter months, and so on. But when you look at various models, none of them is doing as uh, the observations depict. Some are closer than others, but this model here is raining in August all over this region, whereas this region tends to get more rain in July. Okay, so you're starting with models that have a shift in time, let's say, or a wrong amount of rain in the wrong month. This is not considering the total amount of rain, by the way. Most models tend to put less rain on India than observed. So there is a so-called dry bias. And this could be because of ocean circulation issues, because of the ocean atmosphere interaction issues, because of land vegetation issues, and so on. We don't know. We have to. There are many studies arguing for different mechanisms. It could be because of intra-seasonal variability, which is very important here as well. Okay, and then you look at the projections from those models, and you can see that they are not at all on the same page. Okay, many of the models are showing rainfall in August, but they have biases here as well. So how do you use this information? Obviously, again, there are ways to reduce biases, and there are ways to combine past data to do statistical projections to increase reliability. Okay, these are the approaches that people typically take. So I will leave this as a short podcast because I want to move to time-dependent impacts in the next podcast. I'll come back to that a little bit later on. Okay, again, projections are there. These are done by models that are very reliable. They have some issues which can be fixed, and we have no option. We have to make decisions under uncertainty. So we try to make sure that the what-if scenarios provided are usable at local scales. That's the main message.